about capacitors. You see these weird looking things in your electronics. Well, that is, if you open them up, particularly these smaller ones. What are they and what are they used for? Well, that's what this unit is about. The most common one is a parallel plate capacitor. And parallel plate capacitors are fascinating, and they have some interesting characteristics we'll look into in a little bit. If you look at a parallel plate capacitor, we tend to show it on its side with two parallel lines, so it's not very informative, except we're just kind of showing the geometry. You see we have a positive charge and then a negative charge. Now look at what happens. We're going to talk about dielectrics in a minute. See how we polarize the molecules here? This is one way of actually increasing the electric field and the charge stored. Now, capacitors are a very wonderful way to temporarily store electric charge and give very fast delivery. We use these in camera flashes, strobe lights, and it helps to make electronics less sensitive. Here is a typical configuration. You have a battery connected to a capacitor, and you see the two parallel lines. Again, the symbol is as if we're looking at a side of the two parallel plates, and then the bulb. Now, the general formula for a parallel plate capacitor, let me go back, we'll have some charge on our capacitor, some voltage that's actually equal to the battery voltage. So the charge on any given capacitor is equal to CV, where C is a capacitance. We measure capacitance in farads. Now there are other units we can use, but we're not going to. We're going to use farads and just use a capital F. Q is a force of charge, and V is the potential difference. And this is usually the potential difference of the battery that we're using. So the charge on any capacitor is its capacitance times the voltage. Now, how do you charge a capacitor? Suppose I were to turn the battery on. Then, well, before we turn the battery on, there is no net charge. Let's look at this diagram right here. We see, before we turn it on, there is no net charge. Now, what I'm using here is a FET lab. Colorado has some fantastic labs. Now, we're going to connect to the delta V. Oops, sorry about that. Let me fix that. Computers are great. We're going to connect to the voltage. Now, let's make this a positive voltage. Now, I want you to look at the lines. As I increase the voltage, you see how many more lines we get? Look what happens when I reverse the voltage. You see how the lines simply reverse direction? Now, do you see, as I turn the voltage up, the positive charges are removed from one plate and they travel through the circuit. This is the circuit's the only connection between the plates, and they accumulate on the opposite plate. Now, positive Q is always equal to negative Q, and the transfer will stop when the voltage between these two plates is equal to the voltage of your battery. Now look what happens when I disconnect the battery. Not much happens. Let me switch. To discharge the battery, you remove the potential difference. And it doesn't matter what I do to the potential now, the capacitor stays charged. Now, I'm going to take it back. What happens when I reconnect the battery? Watch what happens. Do you see how the charge, it just really discharged very quickly? As I reverse the voltage, watch what happens to the current as I switch back and forth. Do you see how the current is switching? All right, to discharge the capacitor, all I have to do is reconnect a source, and then the charge will move back in the other direction. Now, capacitance is a very interesting word. It is a measure of the ability of a capacitor to store energy. A very large capacitance means it can store a lot of energy. And this is what's really interesting. It's only determined by the geometry of the capacitor. So let's look at what that is. If I have a parallel plate capacitor, the capacitance of that parallel plate capacitor, hard to say, is epsilon naught A over D, where C is, of course, the capacitance. Epsilon naught is the permittivity of free space, which is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Kind of a hard number to remember. Don't worry, I'm going to give it to you. A is the area of one of the plates. So if I have two parallel plates, one here and then, one slightly below, like this, it's hiding under there. This is the area. You remember how to find area? It's length times width. And we measure it in meters squared. And D is the distance between the plates. So if I have two parallel plates like this, D is the distance between. Now, sometimes we replace epsilon naught with epsilon. If we put a dielectric in, which we're going to discuss in a minute, then epsilon is a permittivity of the medium. And when we use epsilon naught, we're referring to vacuum or air. Air is not quite the same thing, but it really is close enough. We don't worry about it. Now, what is a charge on a capacitor? Suppose I have a capacitor, parallel plate capacitor, and I've charged it up. The charge is CV. Once I've found C, it's equal to CV. Now remember, C is a constant for any given capacitor. So once you find C, it does not change. You can change the charge and you can change the voltage, but C depends only on the geometry. Now look at this capacitor here. This is how you'll see a lot of capacitors, kind of cylindrical object. It's got a negative charge, a positive connection, and then this dielectric, which when they're very small you need, these metal plates, and a few other things. How can you increase capacitance? Because that's what we're usually looking to do. Well, let's look at the formula. C is equal to epsilon naught A divided by D. You can increase the capacitance by increasing the area or decreasing the distance between the plates. Now, any charged capacitor stores energy. That's what we use it for. And work is required to move all these charges. The formulas can be a little confusing. The electric potential energy is 1/2 QV, or 1/2 CV squared, or Q squared divided by 2C. Now, I do not remember all these. I remember this one right here. That the potential energy is 1/2 CV squared. Because this one reminds me so much of kinetic energy. Remember, kinetic energy is 1/2 mass times velocity squared. So you can see the parallels here. If you know one of them, you can always use Q equals CV to convert to the other two.